I'm actually with the University of Colorado, but I've been based at the NOAA lab for the last 20 years or so. And NOAA, it's the Space Weather Prediction Center. They're an operational lab, so they provide all of the space weather, operational space weather services for the nation. So a lot of what I've been doing is sort of modeling the thermosphere ionosphere system and trying to understand how it impacts operational systems. And I'll describe some of those to start with, so you know where my focus has come from. So the plan for this morning is that rather than just me talking for 3 hours, which would be very boring, I'm going to talk for about an hour or so, and then we'll have a break and do a bit of a lab. It wasn't originally in the schedule, but we've put together a sort of a thermosphere ionosphere lab so that you can search on that CCMC website and do a fair exercises, sort of things. See, you know, how does the thermosphere respond to geomagnetic activity, the temperature increase, the winds, things like that. And so it will give a bit of a break in the middle, and then of course we'll have the coffee break, and I think there's a photograph being taken or something. And then we'll come back and continue that for a little bit, and then I'll probably have another hour of lectures. So that's the plan. How many of you are studying sort of upper atmosphere type stuff? Just put your hands up if you're studying, you know, the ionosphere, the thermosphere of the Earth, or planets or moons. Who's actually working on sort of upper atmosphere as opposed to magnetosphere or solar? One? Any others? So not many of you. So probably haven't got, apart from the general course, there's not a lot of detail of that. So I'll try and keep that in mind. So I'll be focusing on the Earth's thermosphere and ionosphere. And of course, as a fluid, you can apply the same principles to any of the planetary atmospheres or atmospheres of moons, as long as they behave like a fluid and they're collisionally dominated. But of course, there'll be chemistry differences, so things in the Earth that are important, like the O to N2 ratio, the atomic oxygen to molecular nitrogen ratio is very important for the upper atmosphere of the Earth, because the oxygen controls the production of the ionosphere, and the N2 largely controls the loss. So if you change that ratio between those two species, you have a rather, a huge impact. You can change the ionosphere by a factor of 5, something like that. So although you can apply some of the principles to other planetary atmospheres, some of the chemistry is not going to apply in the same way, of course. Now, you had a great introduction. Sorry, I should just say, this is some of the, hopefully you got a copy through the email of the talk, so there's some of the details in that. But just for reference, you can go back and see some of the, in the textbooks, the chapters that are related to planetary atmospheres and the thermosphere ionosphere. So these are some, and there's some great tutorials as well on that website. I don't know if anybody's had a chance to see some of those tutorials, but there's some great ones. I mean, like Rod Helis, he's just brilliant. You should watch his one talking about electrodynamics and stuff like that. And Stan Solomon, of course, and Jan Soika. And there's a number of others. You can flip through some of those, the list of those tutorials, and you can just listen to them. So you haven't got to wade through all of the slides. You can just listen to them. You get a lot of information from those. And there's a great AGU monograph on modeling the ionosphere thermosphere system that came out only about 2 or 3 years ago, I think. And there's another one that's coming out that's looking more at sort of the longitude and hemispheric dependence that might be useful. So there's some sort of useful references for some of the background reading. So Dana did a great introduction to, where's the ionosphere come from, and how Chapman layers are formed, how the EUV and the UV radiation gets absorbed by an atmosphere. So I don't need to sort of go into that. So I assume that you remember all of that. So that we've got our upper atmosphere of the Earth, the thermosphere. Of course, it starts at about the altitude range that we're covering is from about 100 kilometers. Of course, it goes up above this. This is just showing the sort of the temperature profile, but the temperature gets reaches an asymptote at sort of about 300 kilometers. So this is the sort of temperature change you can get from solar min to solar max. And later on we'll see what sort of temperature change you can get from a geomagnetic storm. And it's the same order. So a storm hits, a CME hits the Earth, or a CIR, and you can get the same sort of temperature change in the upper atmosphere as you get over the whole solar cycle, over 11-year solar cycle. Just in that sort of 12-hour or 6 to 12-hour period, you can get the same temperature change in the upper atmosphere. So that's the bit of the atmosphere that we're looking at. And of course, the ionosphere that goes along with that, you heard about how these F layer is formed and the E layer, and of course there's a D layer down here as well. Well, there was a question, I think, was it last Wednesday, about where do the negative ions come from? And I don't think that got answered. I can't remember who asked the question. But the negative ions come from, and that's in the D region, the electron gets attached to a molecule, so you end up having a negative ion. And you can get all these huge water vapor clusters that can be positive or negatively charged. So there's a whole range of chemistry down in the D region, sort of around, down here at sort of 70 to 90 kilometers. That George Reed has done an excellent review on that in the past. But but for the higher levels, of course, it's the extreme ultraviolet. Its wavelengths less than about 100 nanometers have the energy to ionize the gas, the thermosphere. So they're important. But the ultraviolet, there's a lot of heating and dissociating the O2 to produce the atomic oxygen, and you get a high atomic oxygen concentration. A lot of that is coming from the ultraviolet. The X-rays, of course, get down to the D region. You do get some absorption up at the higher altitudes as well, and I'll give an example of that. And of course, the visible light gets down to the ground. And then you've got all these tropospheric systems that are going on as well. And you get a lot of energy that's propagating up from the troposphere as well. And right at the end, I'll just sort of mention a couple of those. I mean, I'm going to focus on the storm time response, but that's a whole new area, I think, of our discipline, new paradigm of how the upper atmosphere and ionosphere and space weather, because it's actually impacting space weather from the troposphere as well. And of course, you've got the auroral particles that are creating ionization at high latitudes as well. So as I said, I sort of work for the Space Weather Prediction Center, and so we try to understand the system because we want to know how the upper atmosphere is actually going to respond. And there's two main things that we care about. One is the neutral density for satellite drag. The main uncertainty of satellite orbits and all the collision avoidance. You've got a lot of debris up there that is very sensitive. Sometimes they're big, they're light objects, so they're very sensitive to density structure. And so you have to try and track all that debris. And so an operational satellite, they want to know where all the debris is for collision avoidance. And of course, they want to know the density for positioning and for re-entry. And so neutral density is the main thing. It's just flying through the atmosphere, and there's a resistance there's a drag on the spacecraft. But of course, if you have an in-track wind or with going in the direction of the satellite or against it, then that's going to change the effective velocity, and the velocity changes the drag by the velocity squared. So if you have a very large winds, and I'll show you get very large winds in the upper atmosphere, that can have an impact on satellite drag as well, can change the drag by 30 to 40% in some cases. And of course, the other one, the obvious one, I suppose most people think of, is the impact of the ionosphere for your GPS system. It has to, the signals coming through the GPS are delayed by the amount of plasma that it passes. So it's the same as when light goes through a piece of glass. The refractive index of the glass slows the light down a little bit. And the plasma in the upper atmosphere, that signal from the GPS satellite coming through causes a delay on that signal because it acts like a change in the refractive index. And so when you're trying to do the positioning, and the GPS works on timing. So if there's a delay in a signal and you didn't know that there was plasma between you and the satellite, then your position is going to be out. So, and that, it can change your position error by tens of meters. Another one is HF communication. You need an ionosphere to reflect the waves off. Just as here, you want your ionosphere, if you're trying to communicate with somebody over here, then you want a layer to reflect off. And if that layer is changed or goes away and you use the wrong frequency, it will just pass right through. And of course, there's so satellite communications, HF communications, GPS positioning, things like that. They're sort of some of the main space weather effects. So we want to try and understand the neutral atmosphere and the plasma density in such a way that we can help mitigate some of the impact of all those space weather. That's sort of like the background goal of what we're doing. This figure's just sort of reiterating the fact that the upper atmosphere is dominated by neutrals. Most of it is the thermosphere. And we think of the ionosphere as being the upper atmosphere, but the ionosphere is sort of down here, it's sort of 1 part in 1,000, and up here it's about 1 part in 100. So it's generally less than 1% of the upper atmosphere is actually plasma. So it is definitely weakly ionized. So the fact that you're sitting in that neutral gas and the different composition, whether it's oxygen or N2, has a big impact on all of these systems. I wanted to just mention, I'm not going to focus on the response to flares, but of course when you have a CME, there's a good chance that 1, 2, 3 days earlier there was a flare, and of course that flare arrives in 8 minutes, and it ionizes the D region, and we've got this D region product, so you can go on the SWPC website and see the enhancement of the D region, and it affects the absorption, because when you have a radio wave passing through a plasma, the electrons get excited, and then the wave sort of propagates through. And if the electrons don't collide with anything, then that wave travels through the plasma, and it's fairly undissipated. It stays with good strength. But if you excite the electrons in the plasma, and if the collision frequency between the electrons and the neutral atmosphere are high, then before the electron has had a chance to re-radiate to create the wave, that radio wave, electromagnetic wave propagating through the medium, there's some of that energy gets absorbed. And the electrons have to get down to about sort of 80, 90, 100 kilometers altitude, and the electrons at that altitude are combining quite rapidly with the neutral atmosphere. So you get absorption. So when you have a flare, then instead of the wave propagating out, reflecting off the F region and enabling communication, it gets absorbed in the D region. So that's called D region absorption. And so we're interested in what happens for space weather with a flare as well, not just coronal mass ejection when that strikes. So they're very different physical processes that are going on, though. And you also get some of that flare energy gets absorbed up in the higher altitudes, up in the, say, at 200-300 kilometers altitude. It doesn't cause a big change in the neutral density. I'll show you sort of how a CME changes the neutral density in a bit. But a flare has a sort of a fairly modest change on neutral density, sort of 20, 30, 40%. In even the big cases, it's only 50% change in density, whereas a storm, a geomagnetic storm, when a CME hits, that could be a factor of 5. So very different response. This is just some of the measurements of how we observe the flare response using the GO satellite. So I wasn't going to talk any more about flares. So I mentioned before how important the ratio between the oxygen and the N2 is in the upper atmosphere, because the oxygen makes it when you have solar radiation, the EUV. With an oxygen atmosphere, then you have a very strong ionosphere. If you have an N2 dominated atmosphere, then it tends to destroy the ionosphere. And so you can look at these are the profiles. You can see up to about 100 kilometers, all of the atmosphere is well mixed. All of the waves coming up from the lower atmosphere, it's mixing the gas. So you have a uniform mean molecular mass, or you mix up all of the gas very effectively. But by the time you get about 100 kilometers, then they start to, there's not so many mixing processes. There still are some. It's not completely unmixed. But each species starts to separate out with its own scale height, and Dana talked a little bit about this on last Wednesday. So eventually the oxygen takes over here, and so the oxygen is light with a mean mass with a mass of 16, and the N2 with a mass of 28. So the N2 decays away in altitude in density faster than the oxygen. So at around the sort of the middle of the thermosphere, you get about an equal ratio of the N2 and the atomic oxygen. But then here the atomic oxygen dominates, and at the lower altitudes the N2 dominates. So if you change that structure in any way, it has a very big impact on the ionosphere. So you can imagine any mixing process in here that would change this and push the N2, change this profile, will change the ratio between these two species. And the storm in itself creates an upwelling. You can imagine a vertical wind in this region. It's going to carry there's a lot more N2, so it's going to carry a lot of the N2 up in altitude and push the oxygen out the way. So a vertical wind is very effective in this region because it's a steep gradient. And I'll just illustrate that in another figure as well. I probably don't need that one. But if you go up in altitude, you end up in this well-mixed region. The mean mass is constant because it's all well-mixed, and it's the same as it would be up to at the ground. It's the mixture of gas. You get about the same mean molecular mass. Then when it starts to diffusively separate, as you go over to more of the oxygen atmosphere, then you go through this sort of inflection point. And so you can see where that gradient is the steepest in the mean molecular mass is where a vertical wind would have most impact. And that's exactly where some of the storm time circulation and the upwelling that you get during a storm occurs. And then, of course, if you go up further, then it becomes a helium and hydrogen atmosphere. So you have this sort of vertical profile of the mean mass. And just to recap some of what Dana was talking about early on. So we tend to use hydrostatic equilibrium. I mean, it doesn't work for all atmospheres, but it just means that the gravity, the pressure gradient and the gravity are balanced. And so this is the equation for the hydrostatic balance. Hydrostatic balance doesn't mean that it's static and that you can't have vertical winds. You can still have a vertical wind. It just means that the atmosphere responds at the same rate of the energy source. So it'll expand and create vertical winds, but maintain a hydrostatic balance. It's not the same as a diffusive equilibrium balance. So you can still have a separation of species, and it can be out of diffusive equilibrium, but it can stay, and it more or less stays as a hydrostatic balance. It doesn't work on short time scales. So on a 1 or 2 minute time scale, which you can have departures from hydrostatic balance. But on 5 to 10 minute time scales, then the atmosphere is fairly in hydrostatic balance. So, and of course you have the gas law, and I think that was the main point I was wanting to say on here. So the way that the species decrease with altitude, this is more for reference. So we have the thermosphere. It's gravitationally bound. It's close to hydrostatic balance. It's collisionally dominated up to about 600 kilometers. And at some point, the mean free path becomes long compared with the scale height. The scale height is the height that you have to go through before the atmosphere decreases by a factor of 1 upon E, and the e-folding distance. But once you get to higher altitudes, the collisions become so infrequent that it doesn't really behave like a gas anymore. So it's a transition from collisional to collisionless near the upper levels. For the plasma, it's not so important. You can treat that as a collisional medium to much higher altitudes because it doesn't actually have to physically collide for it to behave like a fluid. It can behave like a fluid if there's some interaction like the Coulomb interaction, the longer distance Coulomb interaction. So the plasma you can treat as a fluid out all through the plasma. In fact, I think the magnetosphere is treated as a fluid. So it's not collisionally dominated, but there's an interaction between the Coulomb interaction that is making it appear like a fluid. So if you have a fluid, of course, you can use the gas laws. It has the temperature of a gas, and this is true up to about 600 kilometers altitude. The pressure is a sensible number, and you can use the fluid equations, the same equations that you use to forecast the weather down at the lower altitudes, the tropospheric weather. You can use those same equations up to about 600 kilometers altitude. Some of the terms, of course, are different, and I'll describe some of those. Of course, it's heated, ionized, and dissociated by the solar EUV and UV radiation and the aurora. So there's quite a rich photochemistry, and you get that Chapman profile in the ionospheric layers. But it's only, as I said before, it's only partially ionized. Less than 1% is ionized. And it's not chaotic. As far as we can tell, it's not a chaotic, weather systems are chaotic. You've got the same amount of energy coming in more or less every day, and yet the the troposphere is changing on a day-to-day basis. It's a chaotic system. As far as we can tell, although, of course, you get changes on day-to-day in the thermosphere-ionosphere system, we don't think it's sort of in its own right chaotic. Certainly the physical models don't indicate that it's chaotic. It appears chaotic just because it's responding to all of the stuff coming up from the lower atmosphere. And of course, it's strongly driven by, the chaotic convective atmosphere beneath it, the troposphere. And of course, it's overlain by this strongly ionized and magnetized plasma, the magnetosphere. But the magnetic field, it sits in the Earth's magnetic field, varies with latitude, and it's pretty much, the thermosphere doesn't experience much change in the magnetic field. So we actually use the magnetic field as a coordinate system for the ionosphere, and this is it's mainly a sort of a dipole coordinate system, so you can use that as a coordinate system. So you end up using the electric fields and the current flow, assuming that the B is constant, but it's just a perturbation, so that on short time scales, even the biggest change in B up at high latitudes, when you have an auroral current, you only have about 1,000 nanotesla. So it's a very small percentage of the background magnetic field. And of course, we have strong ion neutral coupling, and you also have these plasma instabilities. So I made that list because I wanted to just ask, you've heard about the solar atmosphere, you have the photosphere and the chromosphere and the corona. So after I just described all of that, from what you've heard of these three regions of the solar atmosphere, which region of the solar atmosphere is most like that thermosphere, all those parameters that I just described? Any thoughts? All right, I'll make you respond. Who thinks it's more like put your hand up if you think it's more like the photosphere. Okay. Chromosphere? Who think it's more like the chromosphere? Okay. So the rest of you must think it's more like the corona, yeah? And some of you don't care, yeah? It's actually the chromosphere. One of the volume 1 of the books, the Heliophysics textbooks, Carl Schreiber and I we sort of were trying to compare, and we did it on a very it was very superficial at the time, and I'll give you a reference to a paper now that has compared and contrasted the chromosphere with the thermosphere, and it's always good to sort of to see the similarity, where do the similarities come from? So it's always good to see that. And so the similarities, they're both partially, believe it or not, it's more ionized, of course, in the chromosphere, but they're both partially ionized over a large part of the chromosphere, and of course, in all of the thermosphere, it's partially ionized. Mostly gravitational bound in the chromosphere, and they're not chaotic in their own right. They're both responding to the convection, both driven by the underlying you know, the photosphere is chaotic. You can see all of the patterns and stuff in the photosphere, and of course in the troposphere. And they're both overlap. You know, you've got the corona and the magnetosphere. They're both these magnetized plasmas that are above the. And the I don't think the chromosphere is strongly driven by the corona, but certainly the ionosphere is certainly strongly driven by the magnetosphere. Both have strong ion-neutral coupling, both collisionally dominated, and they both got this transition from collisional to collisionless at the higher altitudes. And actually both have these Rayleigh-Taylor instabilities. And maybe I'll show you sort of animations of those towards the end to show you how similar. Of course, there's lots of differences as well. I mean, of course, the temperature is hugely different. Although they're weakly ionized, there's still a lot more ions in the chromosphere. Of course, the magnetic field, whereas for the thermosphere, you've got about 1% modulation of the magnetic field, whereas in the chromosphere, of course, you can have factors of 10 and 100, depending on what the photosphere is doing in the corona. The ionization from heat for the chromosphere versus ionization from EUV, the solar radiation. And the ions are a much stronger driver of the system in the chromosphere. And this thing about how we treat them, and Dana sort of mentioned that a little bit before, our sort of two disciplines sort of treat the electromagnetism in a different way. Because we can have a fairly constant B, we can use B as a constant, and we're just looking at the perturbations of B, and so we can estimate the currents and making the electric field a gradient of the potential and things like that. Whereas you have to use MHD using the BV paradigm rather than the JE paradigm, and you'll see that coming up sometimes. And I don't know how much that's been talked about over this last week. And the thermosphere ionosphere is driven from the magnetosphere. Differences. And there's a lot more turbulence in the chromosphere. It's fully turbulent versus the transition to molecular separation. And this is that review. There was a NASA focused science topic that targeted the two systems and how they were similar. And I recommend reading that. It's an incredibly detailed review, but I think it was an excellent review. So where are we? We've got the sun now. How does it drive the system? Of course, you've got the pathway that we're going to focus on today, which is the solar wind driving the magnetosphere and then injecting energy in from the magnetosphere. Of course, you have the direct solar radiation with the EUV and X-rays that are coming directly through to the Earth and ionizing. The UV visible, of course, that gets down to the ground, and then that ends up driving the system from below. Of course, the sun is the energy source, but the variability from below is coming from the tropospheric variability, and the variability from above is coming from the solar wind variability and the EUV flux. What are we doing? So you have this complicated, and you can sort of think of the thermosphere ionosphere, because it's so immediate here, and we can sort of sample it much more easily. We're sort of getting to the point where we sort of understand the system a bit like for weather forecasting. They're not really sort of they're not in a discovery mode so much for weather forecasting. They're trying to improve the prediction of weather for 5 days or 10 days. We're not quite at that level with the thermosphere ionosphere, but we know a lot of the physical processes that are going on in the system. And this is it's a lovely figure. I think it illustrates all the physical processes that we do understand. We don't know sort of their relative balance during a storm and things like that, and we're not very good at forecasting and things like that. But we're sort of getting to the point where we're treating it as a system. It's sort of system science rather than discovery science. And actually, Rod Healis on the CDAR tutorial, he gave a great talk about the difference between that sort of discovery mode and the system science. So, we're looking at the system in rather a different way, perhaps from some of the other regions of the heliosphere and heliophysics. So the main sources for a geomagnetic storm, we have, doesn't come out very well on here, but this is the magnetospheric potential as it gets mapped down, as it appears in the upper atmosphere in, say, around 300 kilometers. You see this, when the CME hits the magnetosphere, it forces, there's an interaction between the magnetic field of the solar wind and the magnetic field of the magnetosphere, and it causes plasma to flow around, pushes the plasma with the solar wind, and then there's a return flow. And so you tend to get these two vortices in the magnetosphere. And if you map that down with the magnetic field, when it comes down to the magnetic field, you end up with these two cells, these positive and negative cells. And I think another question that came up the other day was, how do you measure this polar cap potential? And if you think of this as the electric fields in here are the gradient of the potential. So if you had a satellite that flew across this, then you can measure the plasma drift. And if you assume that plasma drift is just is E cross B drifting, it's just there's no collisions. There's a gyro frequency around the magnetic field, and the electric field will cause the plasma to move in the E cross B drift direction. So it's anti-sunward over the pole and sunward in the dawn and dusk sectors of the auroral oval. So if you can imagine, if you fly across here, you measure the electric field, and so the gradient of then as you integrate out, you can integrate the potential as you go across this. So you can estimate what the peaks and troughs of the potentials are. So you can get that's the cross-polar cap potential, which can be anything from tens of kilovolts to several hundred kilovolts during a geomagnetic storm. So you've got that magnetospheric potential that's mapped down. It looks at the ionospheric potential, which creates the electric fields. Of course, you have the aurora. This is just an example of the aurora from the Tyros NOAA observations. You have a penetration electric field, because when you have a sudden change of this high latitude potential, to start with, it's unshielded. So the electric fields can penetrate down to the equator. Then eventually the inner magnetosphere starts to respond to those same electric fields, of course, in the magnetosphere. Those same electric fields start to redistribute plasma in the inner magnetosphere and shield it. So, so you do have a penetration down to the equator. And of course, the main source of heating is the Joule heating. So there's some of the sources that we're dealing with. And if you look at the energy flow, if you had, say, 1,000 gigawatts of magnetospheric energy coming in as Joule heating, or coming in of some form or another, a lot of it ends up as an electromagnetic energy, and some of it is just the individual auroral particles. They're spiraling down the magnetic field, and then they collide with the atmosphere. So about 20% of the energy comes in as particle precipitation, or the aurora, and then that causes ionization, of course. And then the amount of the Poynting flux, the electromagnetic energy that comes in, a lot of it comes in as Joule heating, which is the expression for Joule heating, but some of it comes in as, because the plasma is moving, it collides with the neutral atmosphere, there's a kinetic energy dissipation, so that it drives that's where the ion drag is coming from. So the ion drag will drive the neutral atmosphere, and so it has kinetic energy. So there's a dissipation of that energy, of this electromagnetic energy as kinetic energy, and it also as just heat, as Joule heating. And of course, then the kinetic energy is that is what's driving the high velocity neutral winds, and then the heat source from Joule heating is what's causing the thermal expansion, the upwelling, and the whole global circulation changed. If you have any questions, don't hesitate to just ask. So when that CME hits, it goes through a whole chain of processes in the upper atmosphere. So first of all, as I just said, the auroral precipitation enhances the conductivity at high latitudes. And the aurora and the increase in that magnetospheric potential, or the ionospheric potential as it appears, these electric fields, they increase at the same time. So the electric field enhances the plasma transport at high latitudes. Then you also get this penetration to low latitudes. The ion drag at high latitudes starts to drive high velocity winds up to of the order of a kilometer per second, and I'll sort of compare that with some of the tropospheric wind velocities so you can get an idea of how a nonlinear system it is. And that dissipation, because the ionosphere is colliding with the ion drift is colliding with the neutral atmosphere, you have dissipation, and so you have Joule heating and particle energy, which are heating the atmosphere, causing a thermal expansion, and so then you'll see a neutral density increase. But then if it's local, then you'll generate horizontal pressure gradients. You heat it in one region and not in another. Then the thermal expansion in one region will create a pressure gradient, and then the wind circulation then tries to balance out those pressure gradients, and so you get wind surges. If it's a very dynamic energy input, you get a lot of winds, and I'll show some examples of those. Then you get a whole change in the global circulation, and then the global circulation causes the upwelling. Remember, because the oxygen is atomic oxygen at the higher altitudes and the N2 at the lower altitudes, any neutral circulation and upwelling is going to transport that N2 and change the ratio between the oxygen and the N2 and affect the ionosphere. So that's causing the neutral composition changes and the negative ionospheric storms, but then you also get a lot of positive ionospheric storms as well. And because of all the wind changes and the conductivity changes, you get a disturbance dynamo. So I'll try and sort of illustrate some of those as I go through. If we go back up to the polar region again, we've got this, we've got a positive and negative potential, and the gradient in the potential is the electric field. And in the upper levels at around 300 kilometers altitude, the plasma will move in the E cross B drift direction. So the magnetic field is down into the board, and you have electric field here from dawn to dusk. And so then the E cross B drift, just from the rule, will give you a plasma transport and anti-sunward. So you've got E cross B, and so that will cause a plasma transport from the day side to the night side. And then in this region, the convection, the magnetospheric convection, or the ionospheric convection is going sunward. Here it's anti-sunward, and here it's sunward. And so the plasma is tending to follow these potential lines up where there's no collisions. And here's a picture of the actual. It doesn't come out very well, I'm afraid. So it's anti-sunward over the polar cap, and then it's sunward in the dusk and dawn auroral ovals. So that's how the magnetospheric transport, what that looks like. So you've got the collision frequency at around 300 kilometers altitude. It's not very strong. It collides about once every, about once every minute, I think. But it's enough just to keep knocking the neutral atmosphere. Every time these ions are moving at, say, a kilometer per second, and every time it hits a neutral, it's giving it a little bit of momentum. And so it starts to drive neutral winds. And this is the pattern of neutral winds. You can see there's a strong vortex here in this dust sector, and a much weaker vortex here. It doesn't really get going. And I'm going to sort of talk a little bit about some of the nonlinearities in the system to try and explain what those differences in the neutral atmosphere response, the neutral atmosphere wind response is. The maximum wind that's ever been observed is 1,400 meters per second. That's, if you do it in miles an hour, it's that. And you imagine a Category 5 hurricane is winds greater than 155 miles an hour. It gives you an idea of the magnitude of the winds that you're dealing with. If you remember, I said if you've got an in-track wind or the impact on the neutral density from an in-track wind, you've got a LEO, a low Earth orbiting satellite, moves about 8 kilometers per second. And so if you've got a 1,400 meter per second, 1.4 kilometer per second change in the atmosphere, that's the atmosphere is, the satellite is moving through the atmosphere that is either moving towards it or away from it. So you can have an apparent density change of 35% as a result of that. So, you know, we need to know what the winds, how the winds respond to know how a piece of debris is, predicting where a piece of debris is going to end up for collision avoidance. So we need to understand how these winds actually respond to this ionospheric convection driven by the magnetosphere. Yes, that's right, yes. Yes, that's right. You're changing the apparent velocity of the satellite through the medium. So the density that it experiences, the drag that it experiences, is not just the density of the medium, but it's the relative velocity, because it's proportional to the density and the velocity squared for the drag term. Thanks, good question. And that asymmetry in the response, this is sort of from quiet to storms, same sort of magnitude of the winds. You notice that this vortex is very strongly developed, and this vortex isn't. So, and the ion drifts are similar, the plasma densities are similar, but there's a different response. And when we first saw these results, and the model was producing these asymmetries, well, what's causing that? So I just wanted to sort of, you know, and this is the sort of thing I think that probably when you're doing your science, you'll have these types of things like this, and trying to understand what causes it, which is, you know, it's just to observe it and reproduce it in a model isn't enough. You need to understand, you know, what causes that asymmetry in the dawn and dusk response. And it's the sort of science question that, you know, you in your career will be sort of trying to address. You know, and you can always sort of, that you try and reproduce an observation with a model. That's just the first step. The main thing is trying to understand it. Because in meteorology, we don't really sort of think of any difference between we have our these high and low pressure cells at mid latitudes, and for tropospheric weather, if we have a high high pressure cell, then the winds will start to go towards, so away from the high pressure cell, and then Coriolis will make it turn round, and the equilibrium is for a vortex of around a high pressure cell, a clockwise or anticyclonic vortex where the pressure gradient is balancing Coriolis. So that's, you know, what we think of for tropospheric balance of forces. And for a low pressure cell, the winds start to get attracted by the low pressure cell. They're going down the gradient, and then it will start to migrate, move to the right, and so the net result is an anticlockwise vortex or a cyclonic vortex. And so, and the reason why you can do that is that these winds are not very strong in the troposphere. So the inertial terms, the sort of the v squared upon r. You imagine, you know, when you swing a conch around on a string, and I suppose you know that these days. But you think of the centrifugal forces and the v squared upon r forces that are operating. And they're not really very big here. They're dominated by Coriolis and pressure gradient. So then there's a symmetry between an anti-clockwise and a clockwise vortex. But it's not really the same when you have these high velocity winds. You've got winds that are 10 times hurricane force, and they start to become nonlinear even with hurricane winds. So it's a very nonlinear system. So you have a parcel of gas that, moving with those sorts of velocity, is moving, it's transporting material, it's advecting material very, very quickly. It's moving through, many degrees in latitude or longitude. So those acceleration terms, the inertial terms, if you like, are very strong. And what I'm going to try and sort of convince you is why you've got this asymmetry in the dawn and dusk response. It's due to these inertial terms in a non-rotating sphere. Okay, I'll get to that in a minute. So we tend to use spherical coordinates. But we have to be careful that a spherical coordinate system isn't an inertial frame. And when you have these large wind velocities, those inertial forces become important. So I just want to sort of give you actually, I'll just go on to the next one for a minute. If you have these are the lines of, this is the spherical polar coordinate system. So you're looking down on the North Pole. So if you imagine if you had say an eastward wind at this point here. Now, if in the equations of motion in a spherical coordinate system, if you had no forces on a parcel of gas and you set it moving eastward, if there's no forces, then that would say it would just stay as an eastward velocity. But where does a parcel go? If you had a non-rotating atmosphere, if you just had a sphere, all you do is constrain it to it has to follow the curvature of the sphere. But if you start something moving off equatorward here, where would that parcel of gas go? Would it go off? Who thinks it would go off around and just follow a constant line of latitude? Where would that parcel go? What would be the inertial motion of that parcel? Anybody have any ideas? Well, it goes off in a great circle. If the fluid doesn't know anything about coordinate systems. So if you just had a sphere and you put an arrow on that sphere and you say, okay, where would a parcel go? Of course, it would just follow a great circle. And a great circle on an eastward wind here would follow a great circle. It would end up going equatorward here and then come back round and end up coming back here again. So you need terms in the equations of motion that allow for the fact that it's a non-inertial system. And these look complicated, and I'll just go through some of them. These first three terms, all they are is just advection. If you're following a parcel of gas, you do the total derivative, and that these all go away. This is just saying, if you're looking at a given position on the Earth, material is sort of flowing across you. And all these terms are just those advection terms or transport terms or inertial terms. I mean, there's lots of different names for them. Pressure gradient, just this is in the pressure coordinate system. So this is the pressure gradient. The Coriolis term that you normally use is this 2 omega v theta cos theta. This is for the momentum equation or the wind equation for the zonal wind, the v phi. But you've got this extra term in here, and all that term does is just make sure that if you had no rotation, it just means that the plasma would go on a great circle trajectory if there were no other forces operating. Then you have viscosity term, and this, of course, the ion drag term. These I should just point out that when you're applying these sort of Navier-Stokes equations to different planetary atmospheres, depends a lot on the actual circumstances. If the atmosphere is very expanded, then you can't use the same approximation. So, and I just wanted to give you a reference to J.R. Holton, An Introduction to Dynamic Meteorology. That's a good book if you're trying to look at the neutral dynamics of a system. But we assume the shallow water approximations. These are the result of using the shallow water approximations. And so we assume that the vertical wind is small compared with the horizontal. Means you can ignore some of the cross terms in the advection. So these are just the first order terms, but there's an additional set of terms. You get the vertical Coriolis force and second order Coriolis forces that you can neglect. And centrifugal forces, just as the Earth's rotating, it's pushing stuff out. And Earth's non-sphericity. and variable gravity. So there's a lot of approximations. So you have to keep that in mind because you apply these same equations to another planetary atmosphere. You have to understand that you might have to add some of those other terms in. So in that case where we had the clockwise vortex, now because the ion drag is actually what's driving the winds in the first place, Coriolis is pushing it to the right. And to start with, if there was no pressure gradient, these winds are so strong, you get the curvature term, the inertial terms are actually trying to, because it's trying to push it in a circle, the curvature terms are pushing it out, the v squared upon r. And so in this case, you get a balance between Coriolis and these curvature terms. So with a clockwise vortex, an anticyclonic flow, you get a balance between Coriolis and curvature. And this is the case for that vortex in the dusk sector, that you get this balance. But if you go to the other sector, and the ion drag is trying to force it into an anticlockwise vortex. Coriolis is pushing it out to the right. This is the northern hemisphere. But the curvature term, because the curvature term is still outwards, of course. So they're both going in the same direction. So it's trying to make this divergent. So that would actually create a low pressure cell in the center of this vortex. So this vortex in the dawn cell is always divergent. So it's always trying to spread out and diverge, whereas in the other sector, it's balanced. So that's the reason why the dusk cell can respond to the ion drag. It's an inertial resonance. You have a force that is a momentum source that's forming a vortex, and that's the natural motion of the gas wants to form a vortex. So it picks up the momentum of the ion drag very readily, whereas in this sector, it's always throwing it out, so it doesn't pick up the momentum very quickly. So that's the inertial resonance. I think I've probably discussed that. I'll try and move on a bit quicker. So as I said, if it's a divergent vortex, it creates these low-density cells, and they're actually low-pressure cells and low-density cells in the center. And you can actually, you see those in the model, these low-density cells, and you actually see them in observations as well. So again, this is a dynamically driven depletion of the ionosphere as seen from a satellite at about altitude on there? Yes, approximate altitude, sort of in the middle thermosphere, 200-300 kilometers altitude. So again, it's for this ion drag case, trying to predict the trajectory of a piece of debris. If it flies through one of these holes, then and you didn't know about that there was this neutral density hole, then the collision can have collision avoidance problems. So I should mention a little bit about this, I think. As I said, when you don't have many collisions say at 300 kilometers, the collisions of the ions with the neutrals, it's enough to give you enough of a momentum source to set the neutrals in motion. But it's not really enough to really sort of divert away from the E cross speed drift. The motion would be if there was no collisions, it would be E cross speed drifting in those two vortices. As you go down in altitude, it starts to collide, the ions start to collide more and more with the neutral atmosphere. So by the time you get to about 130 kilometers, those ions have now rotated towards the direction halfway between the electric field vector and the E cross speed drift vector. Oh, sure, yes. Will do. So as you go down in altitude, as you suffer more collisions, then the direction of the ion motion, and that will be also the direction of the momentum drag, will change in altitude. And so that means, I'm not going to spend a lot of time on that, but there's just a figure here that just shows you what the response would be at different altitudes. But I'm not going to focus on that. I'll just do another couple of slides, and then maybe we'll have a 5-minute break. So the ions are moving through the medium. They're colliding with the neutral gas. They're depositing momentum. But the collisions between them means that the energy of the ions, they're being slowed down. So there's a dissipation of that energy, that magnetospheric energy that's getting down. And it ends up as heat. And one of the exercises that we'll get to in a bit is looking at how that, what sort of magnitude of the heat. But this is just an example of a quiet and disturbed global structure of neutral temperature. And you can see these are the temperature increases. You can see the scale here, just about 6 hours into a geomagnetic storm. So you have a large temperature increase of several hundred Kelvin from this Joule heating, the dissipation of the magnetospheric energy in the form of Joule heating. So you get these large temperature increases at high latitudes. And of course, they're very dynamic. The energy input isn't just a nice steady increase. It's a very variable electromagnetic energy source. So that energy source can drive a lot of waves. And this is just a simulation. This is just showing from minus 50 to plus 50 latitude, from that all longitudes. And you can see how dynamic the neutral atmosphere dynamics actually is. From all of these energy dumped in at high latitudes, and it's creating waves that are sloshing backwards and forwards. So it's a very, very dynamic system. And of course, if you see it in the neutral winds, you're going to see it in the other parameters as well. You can see those winds, and they actually propagate from one hemisphere all the way to the other hemisphere. So it's you can see these dynamic winds. The scale here is about plus or minus 150 meter per second. So the winds at the mid to low latitudes aren't so strong, but you get all these waves. And of course, these waves are going to push the ionosphere around. So, yes, I'll just talk a little bit about, so the neutral density responds as well. And you can see how strong the neutral density, when you have the energy input at high latitudes, you have the increase in the neutral density. And again, it's very dynamic. Those waves are having signatures in the neutral density as well. You get a lot of neutral density increase, which is affecting the satellite drag. And we want to try and understand how that neutral density responds for collision avoidance. So maybe we'll have a 5-minute break just to stretch our legs, and then I'll come back and we'll talk a little bit about the global circulation and the neutral density changes. We've got about another 20 minutes at least, and we can sort of start the lab when we get after I've done a little bit more. But let's have a 5-minute break, and then we'll go on from there. Yes, yeah, that would be good. I mean, I'll give a few more slides before we go into the lab, but yeah, if you could do that. Oh, thank you. Yes, good. Yes, good. Well, it's... There are only 2 stones. Yes. So when you ask for the... Okay. Most of them. Yes, yeah, it's good to have a breath, I suppose. Wait to see. I was looking forward to seeing you. I thought that was great. Various locations that you struck. I just never in my life, in terms of Mm-hmm. Right. Yeah. It took us ages to understand, what was driving that. Oh, good. Thank you. Thanks. Well, that's.
And here's some neat labs coming up too.
Yeah, we'll try. Yeah, we saw that in the.
I just I try to. It's the way that.
Yes. Yeah,
it's in a regime where it just doesn't have strange.
Yeah, I mean, for the viscosity, the coupling that decreases the steep vertical gradients, but the viscosity, the dimensions are so large horizontally that the viscosity terms are relatively small. I mean, it does smooth out, a convection channel, response to a convection channel and things like that. Good, good. Well, I'm glad it.
Probably too late.
Is there anybody else out there? Is there? Are they all in? Okay, good. So I wanted to talk a little bit about the global circulation, because that's the thing that actually creates these large changes in these O to N2 ratio that I keep saying is important for these negative phases. So even though that animation, it appeared that it's just like it's chaotic. It's just like it's sort of sloshing backwards and forwards. There is a net circulation that actually develops. If you had no geomagnetic activity and you just took, say, like the seasonal circulation, the summer hemisphere, I'll do with the pointer. Say this is a zonally averaged globe, summer pole, North Pole in the summer North Pole, say winter South Pole. And you have more heating, obviously, in the summer hemisphere, and so you tend to generate a global circulation. So the upwelling in the summer hemisphere will transport that N2-rich gas to the higher altitudes. The oxygen at the higher altitudes would tend to be transported into the other hemisphere, and then so you tend to build up more of an oxygen-rich gas in the winter hemisphere and a nitrogen-rich gas in the summer hemisphere. Now, so that would be if you had just the solar heating, and if you add the geomagnetic activity, then you add a little bit more energy in the summer pole and a little bit more energy in this northern pole. So this is sort of trying to fight against the whole global circulation from the summer to winter. So that forces it back, and here it sort of enhances this a little bit. But you end up with this position here in the winter mid-latitudes where you have this strong downwelling and increase in the atomic oxygen. So this is the O to N2 ratio, so you have more increase in the atomic oxygen in this region. So it's molecular rich here, and now it's molecular rich here again, but then it's oxygen rich in this bit. So that would be sort of a moderate geomagnetic activity, and as you enhance that geomagnetic activity, you move these boundaries of where these reduction in the, increase in the oxygen to nitrogen ratio. So here you have an increase in the nitrogen, and here you have an increase in the nitrogen, and here you have a decrease in the nitrogen. So you have that whole global circulation and the storm time circulation, which is creating the neutral composition change. And there's some great observations from, on the time satellite, there's the GUVI instrument measures exactly this parameter, this O to N2 ratio. And so this is, so it's sort of like summer-like here, so you have upwelling and this reduction in the O to N2 ratio. So you've increase in the N2, so the O to N2 will decrease. And this is that band at winter mid-latitudes of enhanced O to N2. And this would be sort of like the moderate activity or quiet. And then as you enhance the upwelling in the polar regions during a storm, that carries the N2, increases the N2, again reduces the O to N2 ratio, and here you have strong enhancement as well. And so you generate a more sort of equinox or more symmetric pattern because of the global circulation from the high latitude heating, from the storm heating, has created this structure. Now, where did I get to? We'll see how many more I want to try and do. So, if you enhance the N2, and this is an image of showing where this oxygen depletion is, and so you have an enhanced N2 in this region, and if you have an ionosonde, a ground-based ionosonde, measuring the F region, that peak F region plasma density, the ionosphere is completely wiped out in that. You lose 80% of the ionosphere in those regions. So it's a very effective recombination rate when you enhance the N2 during a storm. I think that was as far as I wanted to go for. And this again just shows how dynamic it is, but I don't think we need to go there. That's just another. So you've got these for reference anyway. So you see a very large depletion. This is sort of the diurnal variation comparing an ionosonde in the southern hemisphere in Canberra, and here there's one in the northern hemisphere in Asia, and you see this diurnal variation and the model simulations, and then when you get the geomagnetic storm, you completely wipe out the ionosphere in those mid-latitude regions where the upwelling of the N2 can manage to get to the mid-latitude region. I think that was as far as I wanted to get. So let's we'll have a break for a lab, I think, and then so I'll give a few introductions, and then you can start working on some of the lab things, and then we'll probably carry on that after the break for about half an hour, and then I'll go into some of the positive phases of the storm. So this section is really just sort of trying to show how the ionosphere is embedded in this neutral atmosphere, and the winds of the neutral atmosphere, the temperature and the composition of the neutral atmosphere is very important for how the ionosphere responds in creating these negative depletions. There's a whole electrodynamic response of the ionosphere as well that's creating the positive phase, and I'll talk about that when we come back, after the lab. But I do want to skip out of here and give a few introductory slides to the lab, and then there's just about 3 exercises to try, and we'll see if it works. And if we go to the lab. And the lab, I'm using this, the model that a lot of these results have come from. It's not a perfect model. It sort of does some things well, but it does these wind response, density response, and the negative phase composition and negative phase reasonably well. It doesn't really do the ionosphere very well. So for the lab, I'm going to focus on the things that it does better than the other. So we're trying to improve that in other models. But it's a global thermosphere, and it's a global ionosphere as well. But the ionosphere is sort of made up of 2 parts. There's a plasmasphere model with closed field lines, and a high latitude ionosphere with open field lines. So but it is a global model though, and then we of course drive it by. We're going to be doing the response to geomagnetic activity, where we enhance the high latitude electric field and the auroral precipitation, dumping in a lot of energy, just do a simple step function increase. Well, that's just showing that the magnetic coordinate system, that it's based on a magnetic coordinate system for the ionosphere. And I think we've sort of seen some of these background structure that you can see all of the. I think, do you have a copy of these? Did you get a copy of these through email? Yeah, so you can go back. I don't need to spend a lot of time on that. So what we're going to do in this, it's a generic storm. So it ramps up to a sort of high latitude electric field and auroral precipitation that is probably about like a KP8. Are people familiar with the KP index? I assume people are. I mean, it's an index that goes from 0 to 9. So the biggest storms that they measure are a KP of 9. Geomagnetic storms, and so this is sort of not the strongest of storms, but a reasonably strong storm. And you just put this storm forcing on at high latitudes for 12 hours. So we just have an increase ramps up over 15 minutes. It's on for another 11.5 hours, and then it just ramps down for 15 minutes. So we're going to look at how a lot of the neutral atmosphere, the temperature response, how the winds respond, how the neutral composition responds, and of course, since you've got an impulsive input over the first 15 minutes, you have these waves that propagate. So we can have a look at those. I don't think I'll spend a lot of time going through, but just at some point you should read through some of these. You don't want to think of a model as being the physics. If you can simulate something with a model, it doesn't really tell you what the physical process is. It's the first step. You want to try and get agreement between the model observations, but you can use the model, once you've got agreement, you can use the model to unravel the physical processes that are going on. But that's not the end result to get a good model data agreement. And of course, they're sophisticated tools, but they're not the science. So just like a complex instrument, if you like. And also make sure that there's bugs in all codes. So if it doesn't make sense, and if it doesn't sort of make sense physically, then, treat them with caution. Don't just sort of think that it's right. Don't sort of publish things unless you have a good physical insight of why something happens. And of course, they have all these limitations. But it does do some things well. And these are the things that CTIP does do well. And you can go back and. But I wanted to sort of do a lab to introduce you to. It's another resource. If you wanted to go and sort of say, what actually happens in the thermosphere, ionosphere, and you can go and look at some of these simulations, and they're all online at CCMC, and you can go and do this back at home whenever you like. So I'm just skipping through these. So these are more for reference. So we're doing this generic storm, 12-hour increase in the magnetospheric sources. The storm commences, it's important because you can find the bit of the time sequence. Storm commences at 12 UT on March 21st. So you'll have to sort of skip through to the beginning of the simulation. For some reason, it sort of defaults to the end when you click on the time on this interface. And so you're going to be looking at the storm response, but you can look at the difference parameters, which are all in the list of parameters, they're all RD something. So RDs underscore TN would be like the neutral temperature, difference between the quiet and storm. And so those parameters that we want to, and I'll go through one example and then it'll get you going. So if you want to look at we're using a pressure coordinate system in the model. It's only got 15 levels, so you haven't got to search around a lot. But if you wanted to, when I was talking about 300 kilometers altitude, where the ions are moving in an E-cross-B drift, then that's around pressure level 12. So remember pressure level 12. Then as you go down in altitude, the E region is down about pressure level 7. And then you go down to then you get very, very small responses down at these sort of altitudes. Well, that's one of the things. And you've got I think you've got the list of variables to sort of work out what they are. And we want to choose the date. And this IP is this pressure level. So to start with, if you want to just set that to 12, I think it's automatically set to 8. So you just need to start with, just change the variable, change the time that you're looking at, and the IP level, and the variable, and then just there's a button for update plot. These are the variables which I think you've got. So let's just, if we could just go to, I'll just sort of run through there first. I think you've got, okay. Did I have that? Yeah, so if you go to this lab, this is the, have you got the link to that, or are you already there? You're way ahead of me. Okay, so go to this website. Have you got all that up? Yeah? Oh, you have? Good. Okay. So you've already got to there. So if I try and go to that myself, then we can just try to... Right, so yeah, you go to the runs with artificial conditions, the storm time run, then we want the 3D right on this. Okay, so you want to go down and change the parameter to be displayed. Let's start with the temperature. No, let's not do the temperature. Let's do the change in the temperature. So if you go down to the bottom of these, you've got these RD terms, and they're all differences. And if you go to RD temperature, there, RDTN, you click on that one. Oh, is it? Okay. Well, what did you say in the procedure? Just okay. Well, either. So I mean, this is what you want to do. Just play around really to see what's happening. So then you need to go down to the right. So this IP, it's set on 8, which would put it around 140 kilometers. So if you just edit that to 12, and then we want to go to the right time. And this is annoying because it's you have to go. At the moment, it's on the 1st of April. So if you just go back right to the start, and we'll go back to, the storm is actually on the It starts at 12 UT on the 21st of March. Oh, that was pretty quick. So this is the start. So the first 12 hours, nothing much happens. Then the storm starts at 12. So if we just go, say, 6 hours into it, let's just go 3 hours into it, see how long it... So if you go to 15, so that will be 3 hours into the start of the storm, if you click on that time. And now if we update plot, and we keep our fingers crossed, oh, that's good. So you can see some of the sort of temperature changes. So this is the storm minus quiet, so you can get a feel for the sort of the amount of temperature. So given that, then there was three pages of exercises. So just try and see how you get on looking at the temperature change. Did that make sense? Was there anything specific for questions now? Just start sort of looking through those, like the temperature change and how long it takes to get to the latitude, things like that. So just try a few of those exercises and just give me a shout if you get trouble. So you can do that for a bit, and then I think we're going to have a photograph or something. We'll have a break, but then you can come back and sort of work on that, and for about till about 11 o'clock, I suppose it will be, won't it? Then we'll go back to the lectures. Yeah. It's just the difference. I think originally it was what CCMC described the difference between the storm and the quiet. If you go to the original storm runs, it would just be you could look at the TN, that would be the actual temperature, the total temperature. Yeah, they're all difference fields. Yeah, the D is for difference, and R, I suppose, sometimes it's ratio, but in this case, it's just an absolute difference. Anyway, see how you get on, and then we'll... So I just had a question. Did anybody find out how long it took for the temperature, the first response of temperature at the equator? How long did it take? Did it get there in 1, 2, 3, 10 hours? Anybody get a feel for how long it took for the temperature to respond at the equator? Huh? Hour and a half? Okay, was it that fast? Okay, okay. So judging from the time it took, can you get a feel for how fast that information must have propagated through the atmosphere in some way? And if it, say if it took 2 hours to get from, if you had a source region, if the source was up at high latitudes and you see it at the equator, you've got to move that distance in meters in, say, 2 hours. What sort of speed does that imply? Well, if you just do the calculation and the distance over the time, say it took 2 hours and there was that number of seconds in an hour. So that's the number of, that's the speed, the velocity that the information would have to take to get to here. And that ends up being about 900 second. And if you look at the winds here, they're more like 1 to 200 meter per second. So what does that tell you about what the mechanism is for that information to get from here to here? What sort of things can travel faster than the bulk flow is only going at about 100 or 200 meter per second, but something is moving. What might be moving much faster? Right? Yeah, or just a gravity wave. It's not even just a gravity wave, but it's some sort of wave front. So it's like when a tsunami propagates through the ocean, the velocity of the tsunami is much faster, obviously, than the tides and the current flow and things like that. But you can have a wave that propagates. So that wave information is propagating equatorward at the speed of a gravity wave, and that can be, it's just less than the sound speed. The sound speed is usually a little bit higher. So this is the gravity wave propagation. I think in this case it's usually, sorry, yeah. Yeah, so the gravity wave propagation is different. There's a bulk flow, and then there's the gravity waves. So so from that, if you now go and sort of do the same sort of thing with the neutral composition, and see how long does it take for that neutral composition signature to get here? Does it respond in the same way? There's a sort of a large composition increase here, and so that was the exercise too, was to look to compare it with the neutral composition change, which we know is important for the loss rates. So if you plot the change in it's RD, I think it's RMT. RMT is just the mean molecular mass. And you can, if it's a mixture of the oxygen and the N2, it's got to be somewhere between the masses of these two. So they're usually sort of around 22 or something like that for the mean mass. So if you look at the change in mean mass due to the storm, you might have a change of 2 or 3 AMU, something like that. So have a look at those differences in the RMT and see how that propagates equatorward. To see whether, is it the same mechanism as the temperature effect, or is it another physical process that's carrying the composition? Try that next if you've got. What about another minute, 10 or 15 minutes? Anyway, any other questions on? So for the neutral composition, did people sort of get a feel for how the neutral composition changed? This increase in the N2 at high latitudes, did that get to the equator in the same way as the wave? Right. So it's a different physical process going on for the neutral composition change. The fluid, like the thermosphere, can you can have a wave field that it supports wave fields, gravity waves propagating. But the neutral composition actually has to, and when a wave comes through, you see a strong temperature signature. You don't see a strong composition signature to a wave. It's not really changing the neutral atmosphere. The neutral atmosphere might go through an oscillation, but it's not changing the neutral composition on the pressure level. It's the thing that's actually changing the ionosphere. So the physical process that's transporting the... So what do you think the physical process is that's actually transporting the composition? So it's not the wave. So what is it that's causing that to move equatorward? Does anybody know? Remember those terms in the equations of motions? There was the advection, exactly. So it's transport, the advective transport. There's a circulation from the high latitudes to the low. There's a whole global circulation, and it's transporting that into, slowly upwells it and slowly brings it equatorward. And that boundary between the downwelling, where you've got the decrease in the mean molecular mass, so the downwelling is the enhancing the oxygen, and whether you've got the upwelling and you're enhancing the mean mass, so you've got more N2, so the mean mass goes up. So you have that, slowly the meridional winds will transport that boundary. And you see there's quite strong longitude dependencies in that boundary because of the longitude dependence in the source region, so that the magnetic pole is sort of tilted towards the equator here. So the sources are further equatorward here, so that the winds and the transport of the neutral composition sort of penetrates further equatorward in this sector, and then the magnetic pole in the other hemisphere is in this sector, so it's pushing it. So it's a different physical process that's transporting the neutral composition. And then, of course, if you were in this region, you would see the N2 would destroy the ionosphere. And so if you looked at some of the neutral, the plasma densities, you should see some depletions here. Okay, so it's now 11:15. We're going to have another break. But you can carry on working or go and get a cup of coffee, and we'll start off the formal lectures again in 15 minutes. But if you have any other questions currently on this, I mean, you can keep working on this, and you can do these, if you're got another science question, you can just go and interrogate these model runs. Was there any other announcements? Or?
I had 2 announcements.
Okay.
One, as part of our ongoing evaluation of the summer tomorrow,
Have you come in for this afternoon session thing? Have you come in for this afternoon session thing?
I'm not doing anything because I'm teamed up with Nick, and Nick's going to drift away from this kind of speechification that's going on this afternoon about the 10th anniversary. He's going to
You're going to ask a complicated question again, aren't you?
Okay,
Oh, it's
sorry.
getting worse.
I know, I'm sorry. You don't have to answer it, but, okay, so I did the same
15
plot.
seconds. So hopefully with the lab and what I talked about before, you get a feel for how the dynamics of the neutral atmosphere is responding, and the importance of this O to N2 ratio and this composition change and how it impacts the ionosphere. So from that information, you should be able to get a feel for why, if you look at the seasonal, the summer, winter, and the local time variation of the ionospheric response at mid-latitudes to a geomagnetic storm, you should have a feeling for the physical processes that are actually driving it from these composition changes. This is some results done by Alan Roger in, it's a southern hemisphere station, and it's an ionoson looking at the F region peak. And what they're plotting is the change in the plasma density, so it would be a positive or negative phase. It's the natural logarithm of that as a function of season. So it's the southern hemisphere, so December here is summer, and July is winter. And then there's the diurnal variation. So it tells you what the seasonal, summer, winter, and diurnal, like in the early morning or dusk, changes in the plasma density would be as a result of a storm at mid-latitudes from just these physical processes that we're talking about. And what you should be able to sort of answer is, why does the negative phase peak in summer? In that case, I also showed you that there's a circulation from, even without a storm, there's a circulation from the summer to winter hemisphere. So if the storm creates a composition bulge, the circulation is going to carry it equatorward in the summer hemisphere, whereas in the winter hemisphere, the wind's coming towards you, the background circulation is coming towards you, and it's always going to restrict how much you can transport that plasma and create the negative phase at mid-latitudes. So the negative phase always peaks in that summer hemisphere, and the positive phase in the same way. The positive phase, it stays where the oxygen-rich gas is. And in the same way that there's a diurnal variation in the winds. The winds, it's the Earth rotating, the thermosphere heated on the day side, creates poleward winds, and then you go around to the night side, and then the winds will be coming towards you. So you've got that diurnal variation of winds as well. And so again, if you create a composition bulge, a bulge of increase in N2, that bulge, as well as getting transported from the summer to the winter hemisphere, is actually being modulated by the diurnal variation of the winds. And I won't go through the details in here, but all those signatures of these three things. So it's how, and it's the importance of that transport term, the advection term of the neutral composition, and the impact on the ionosphere. So hopefully you'll be able to sort of understand that from the physical processes that we've been talking about. So now I wanted to go on to some of the positive phases that you see, the increases in plasma density. You get some positive phase from this enhanced, if you have an oxygen-rich atmosphere, then you have a positive phase. But some of the big positive phases actually come through the electrodynamics. And we always used to just look at the ionosphere from ionosons from the ground and look at the F2 peak. But it was hiding a lot of the plasma density changes. A lot of the plasma density was actually occurring on the top side. There was this storage of plasma that you couldn't see because the ionoson works by sending a radio wave, HF radio wave, and it can't see the topside profile. It will get reflected when the critical frequency of the plasma matches the frequency of the radio wave. But once you're beyond that peak, the F region peak, it just propagates up. And so you don't have any information about the plasma storage. But there was a new technique. We're now using ground-based GPS, and that is recording the dual frequency GPS signals. The difference in the delay in the two frequencies gives you an idea of the changes in the total amount of plasma along the line of sight from a ground-based observer up to a geostationary satellite. So it's given us a different window on the ionosphere. And so then we started to see these big bulges of increased plasma density at mid-latitudes, enhancements of the equatorial anomaly that we could see some of it with the ground-based ionosondes, but there's this whole new set of phenomena that we started to see that we needed to understand. And they tended to be very large positive changes. So this is just an example of, this is actually a really modest storm. These are sort of maps of the total electron content, this integrated total electron content going up through the ionosphere, all the F region, the top side and the bottom side. So it integrates up. And you can see that these are difference maps, I think. So you see these really large increases, even for quite a modest storm. And it just so happened that this is over the continental US. Can't see the map very well, but you can see, you can just see them here. So you can see this is over the CONUS. So, and these are the ground-based GPS stations that are used to map the total electron content. You can see that even for quite a modest storm, you can get some quite large changes. But it just so happens that if you're in this sector between about 12 noon and dusk, and that was the UT when the storm actually hit, put the CONUS in this sector where you see these large increases. So we want to try and understand, well, what's causing this large increase? And it responds very quickly within an hour. You get quite a large increase just in this local time sector. So depending on which longitude you are, it depends when the UT of the storm actually hits, whether you happen to be in that sector. So let's try and understand what's causing that big increase. It occurs in this region, and you remember the plasma motion is this vortex of ionospheric plasma in these two sectors. So here, now you've got the Earth rotating. So if you had if there was no electric field, then the plasma co-rotates with the Earth. What actually caused that co-rotation is actually an interesting science problem. But let's assume that if you had no electric fields in the ionosphere, that parcel of plasma would just rotate with the Earth. So if you are here on the day side in sunlight, then that parcel of plasma would just rotate with as the Earth rotates, it'll just move around here to dusk. Then it will keep moving around, of course. But now you've got this, you're in this region where the plasma is being advected now towards the sun or towards earlier local times. So you've got these velocities might be, a few hundred meters per second, and even on the sort of the equatorward edge of the auroral oval. So you've got the Earth's rotation is trying to move it that way, and then the plasma convection is moving it in the other way. So it just stagnates the plasma. The plasma just sits there, and it's on the day side, so it's in sunlight. So it allows for the plasma to just increase and increase because it's just stagnating in this sector. And if you add another effect, that you can see that as it comes around here, sort of into the noon region, the plasma tends to have a poleward motion. And if you have a poleward motion, you can't see it very well here, the plasma is moving with respect to the tilted magnetic field, and you're moving the plasma driven by the electric field moves perpendicular to the magnetic field. So it moves perpendicular here. And you can see this has a vertical component. So as well as being transported horizontally, it's actually tending to raise the plasma up to higher altitudes. If you remember the argument about the changes in the N2, you're taking it out of the N2 rich atmosphere. So you're storing plasma on the top side. So you're not only stagnating it in this region, you're also sort of pulling it round and you're storing it. So that's the reason why you have this big increase just in this local time sector for quite a modest storm. When it's expanded into that mid-latitudes where the magnetic field is tilted, then you're storing it in the top side. So that's why you have that. So in this sector, the co-rotation competes with the sunward plasma convection. The ionosphere stagnates in sunlight, so there's strong ion production. And then the small poleward motion raises the plasma to higher altitudes because of this effect. And that takes it to a region where there's less recombination. There's less, taking it sort of out of the nitrogen-rich atmosphere. So you're storing this plasma on the top side, and you might not see it from an ionosonde, but you see it from the GPS observations. And this is an example where you've got all of those things going on. You've got this buildup of plasma during a storm, this effect of stagnation. You've got these, the plasma convection then transports this plasma over the pole. And then you've also got these regions of negative phase. So this is the depletions that you get, because in the meantime, you've got all these N2 rich gas. So if you're not in a region where you're enhancing the plasma, you might be in a region where you're depleting the plasma. So you have these steep gradients across these, which have big impacts on aviation and space weather. So that's sort of one of the mechanisms for the positive phases that you get from this stagnation effect. Now there's another one. When you get down to the equator, this is the shape of the magnetic field at the equator. And the reason why you have these equatorial ionization anomalies is because you have the eastward electric field. If you have an eastward electric field and the horizontal magnetic field here, and if the E cross B drift causes the plasma to rise in altitude, and then it will diffuse across the magnetic field to create these anomaly crests. And so that's what creates even in the quiet time, it creates these equatorial ionization anomalies on either side of the magnetic equator. From the eastward electric field here, and the E cross B drift raises the plasma and creates these anomaly peaks. So you've got that happening, and you create these equatorial ionization anomalies even during quiet times. Now, if you enhance that, if you have I talked about the penetration electric field, so if you have an enhancement of that eastward electric field, then you can enhance might be a quiet anomaly peaks like this, but then if you enhance that eastward electric field on the day side, then maybe you have much stronger anomaly peaks and this large depletion region right at the magnetic equator. So that's so you can have an enhancement of the equatorial ionization anomaly at lower latitudes. So you have this mid-latitude effect, and you have the low-latitude effect as well. I don't need to labor that. So we have, this is to give you an idea of what the penetration field actually looks like. This is incoherent scatter radar at the magnetic equator, and it's looking at the vertical plasma drift. That eastward electric field with the horizontal magnetic field causes an upward plasma drift. And so this is what that plasma drift looks like. During quiet times, it'll have a diurnal variation that looks like this, upward during the day from the eastward electric field, downward at night, and this is a small increase at the pre-reversal enhancement. Now you have a storm, and you have this sudden increase in the high-latitude plasma convection, and that gives you a pulse of eastward electric field down at low latitudes. This is sort of in the afternoon sector. And you're getting 100 meter per second. That's equivalent to just it's not very big. We were looking at sort of 50 millivolts per meter up at the high latitudes. Here we've only got 2 or 3 millivolts per meter, but it's enough to transport the plasma up and create this much stronger equatorial ionization anomaly peaks. So you've got these two effects going on, and they sort of merge, but you can sort of see both. This is some observations from a polar orbiting satellite. From the CHAMP satellite, it's about 400 kilometers altitude, and it's got a GPS receiver, and instead of being on the ground, it's now up at 400 kilometers, and it's looking upward to see, measuring this storage of plasma. This plasma gets stored in that dusk sector, from both those mechanisms. The eastward electric field creates those anomaly peaks to be stronger and raises the plasma up, and the mid-latitude effect creates that peak as well. So before the storm, this might be your topside plasma density. And during the storm in this sector, there's these successive passes at different universal times, but they're all sort of in that sector between about 12 and 18. In that dusk sector, we're doing 12 magnetic local time and dusk. And you can see these huge increases in the total electron content. It's getting up to over 300 TEC units. TEC units is 10 to the 16 per square meter column abundance. So these were some of the TEC increases that we just weren't seeing before from ground base. But now with these new eyes on the ionosphere, we can actually see these huge increases in plasma density. And so here you see, those are not quite time anomaly peaks. And here you can see the anomaly peak, how it's moved with the stronger, from penetration electric fields, you get these much larger anomaly peaks. But then you also see these features at mid-latitudes as well, and that's that other effect that's going on. So you can imagine if you had a really strong storm, you're just really merging those two physical processes, that mid-latitude convection effect and the increase in the equatorial ionization anomaly. So you would, and it's somewhat happening here, they're sort of combining, but you can still see signatures of both the physical processes going on. But you can see that there's electrodynamic processes very different from what we were talking about in the first hour of the neutral composition and the neutral atmosphere affecting it. Much less dependent on the neutral atmosphere in this case, but you're storing the plasma in the top side out of the ionosphere, and due to the production, solar production, but then being stored up in the top side. And these are just another way of looking at it. So we can study those, so you can definitely see the very distinct. There's one signature here and one signature here. Same sort of thing, polar orbiting satellite looking at the changes in the TEC. What the global picture looks like. So now I want to talk a little bit about another changes in the electric field that you can get from, we talked about how the neutral atmosphere changes, the neutral winds, the wind surges, whole global circulation change. And a long time ago, Blanc and Richmond, they tried to work out this, they call it the disturbance dynamo. Disturbance being geomagnetic disturbance, and the dynamo is the fact that you've got a plasma, the neutral atmosphere is flowing through that plasma, it pushes on the plasma, creates any divergence of the current that is produced by that, the winds pushing the plasma, creates a polarization electric field, and that is creating electric field, and then that electric field can then be mapped to higher altitudes, where it again drives the plasma. So in the storm time, what happens during a storm, we saw that the equatorward winds, we saw the equatorward winds, and they, from the Coriolis action, if you have an equatorward wind in the northern hemisphere, the equatorward wind will drive a westward neutral atmosphere drift. That's what the Coriolis will tend to create, move to the westward direction. So the equatorward winds increase the zonal winds at mid-latitudes through the action of the Coriolis force. And these are wind-driven currents from the Peterson and Hall conductivities and the zonal winds and the meridional winds. The theta is the meridional and the phi is zonal. The sigma 1 is the Peterson conductivity, and the sigma 2 is it should have been sigma 2, sorry about that. It was the Hall conductivity. So these are the current flows driven by the neutral winds, and these are the current flows driven by the electric fields, the two components of electric field. So the zonal winds, so we've got zonal winds creating a Peterson current. So we've got the zonal winds here, and this is the Peterson conductivity. So you generate a Peterson current from the zonal winds. So that drives an equatorward current from the wind effect, and also those original meridional winds, equatorward meridional winds with the Hall conductivity, is also adding to that equatorward current. So you've got two effects that are creating an equatorward current during a storm. And so that current causes a charge buildup at the equator, which is trying to balance that wind-driven current. And so now you've got an electric field. So now the plasma is going to now respond to that electric field. And so now in the eastward Hall current, driven by the poleward electric field. So you have an eastward Hall current driven by a poleward electric field with the the Hall conductivity. So this is the electric field, the polarization electric field that gets generated, and then that will drive an eastward Hall current. And so what it's doing is actually it's reversing what the normal the normal dynamo effects of the quiet time circulation. So it actually it decreases the. Actually, have I got a figure showing that? So it changes the quiet time. It's called an SQ current system. It's the quiet time wind-driven dynamo without a storm. So it tends to counteract the quiet time winds. And it ends up being very dynamic. This is the eastward electric field that builds up. Remember, the eastward electric field causes the plasma to rise at the magnetic equator. And so, again, it's very dynamic, and it's not just this slow build-up of the zonal winds at mid-latitude. You've also got very dynamic meridional winds that are driving these wind-driven dynamo effects from meridional winds this term and from the build-up of the zonal winds from the Coriolis force. And so you can see these large changes in the eastward wind. When you have a large increase in the eastward electric field, like that would enhance your anomaly peak. So the dynamo effects the neutral wind dynamo is adding to those and competing with that penetration electric field, and you can see some balance between them. So here is that penetration electric field, but in the observations on the night side, you can see, and this was the normal downward, the westward electric field, which would cause the downward drift. And remember, the storm circulation reverses that quiet time or the quiet time SQ, which is what's driving this, and it actually reverses it. So this downward plasma drift ends up being an upward plasma drift. And that's what you get from that numerical simulation in the CTIP model. You get this upward drift on the night side, eastward electric field on the night side, because we're trying to reverse this normal circulation pattern. So it reverses it. So you can see the effects of the dynamo electric fields adding to all of those other effects. So if you have, now I want to talk a little bit about some of the other things that happen in the ionosphere, ionospheric irregularities. If you have a strong upward drift, it raises the plasma to higher altitudes. And if you're now on the night side, and you have some process that's taking your plasma and raised it to higher altitudes. So normally it would be a nice stable F region layer that was in balance with the production, diffusion, and gravity. So you would have that layer that would be nice and stable. If you're now on the night side and you raise that plasma up to higher altitudes, now it's sort of gravitationally unstable. It wants to move down, but at the magnetic equator, the magnetic field is stopping the plasma from moving down. The plasma can't move through the magnetic field unless there was an electric field that pushed it. So it's sort of suspended there, sort of unstable. But then if you have some modulation, like a gravity wave that's coming up from the lower atmosphere, that's causing an undulation on this bottom side. You've got this dense plasma above and the tenuous plasma beneath. If you've got something that just creates a little bit of a ripple in the plasma density, the gravitational, the current, there's a G cross B ion drift from the gravitational force down, trying to push the plasma down, and the J cross B current. So there's a gravity-driven current that's across these bulges. So in this dense region, there's a current going across here. So, and then it can't flow through this lack of plasma here. So you get a buildup of plasma on this side of the ions, the positive ions, because the electrons really aren't really so much affected. So you build up the positive ions on one side of this bulge, and it's negative on the other side. So now you end up with a gradient across here.
and the E cross B drift of that electric field is actually upwards. Well, here's the electric field, and the E cross B drift for that is upwards. So the wave sort of is trying to push that plasma up and down, and as soon as you push the plasma, you create that undulation. You generate electric field, which is reinforcing the movement of this upwards. So it just keeps going. And that's what it looks like in a numerical simulation. You can see the plasma rising to higher altitudes. It's unstable. And so these low-density plasma starts to percolate through. So the heavier plasma, the denser plasma wants to move down. And so it enables the plasma to exchange places. And these things happen even during quiet times, but during storms, they occur where that night side upward drift was occurring. You can get ionospheric irregularities that now jump out at post-midnight as a result of this process. How are we doing? And so what that looks like in some of the images from the FUV images, you can see, that doesn't come out very well because of the projector, unfortunately, but you can see depletion, these depletions of plasma, these bubbles that percolate through are seeing as depleted air glow features. This is another numerical simulation of it. And this is what it appears like if you've got a ground-based radar system, like at Heckamarka, a coherent or incoherent radar system propagating through and getting the reflection off all of these bubbles that are created. And you can see them a little bit in here. This is image from the International Space Station. So we've talked about the different ways that you can create the positive phase from that mid-latitude effect, from the penetration electric field enhancing the equatorial ionization anomaly. The electric fields driven by the dynamos can cause increases in plasma density. And then you've got the impacts on all of this, the structure of the ionospheric irregularities. So these are all in addition to all those dominant neutral atmosphere effects. But one of the things that, of course, we needed to create these undulations in the ionosphere. And we think that a lot of those undulations are actually coming from the lower atmosphere. So just in the last 10 minutes or so, I just wanted to show you some examples of how space weather can also be driven from the lower atmosphere. You can see that it's impacting these storm time changes and how you're going to get irregularities anyway, because you need these sources of waves propagating up from the lower atmosphere, and they create sort of undulations. We can see it here, the undulations created by wave fields that are coming from the lower atmosphere. And every time you have one of these sort of waves coming, and then you get irregularities sort of growing out of those. So what can drive those? So you just think about how much energy there is in the lower atmosphere compared with the upper atmosphere during a storm. If you look at the amount of solar wind power that's hitting the magnetosphere, it's the order of about 1,000 gigawatts. About a terawatt of energy power is actually striking the magnetosphere. And a lot of that energy actually gets down into the upper atmosphere and was creating all the things that you were looking at in the lab with the temperature increase and the waves and things like that. But if you look at the amount of solar power that gets to the troposphere, it's 5 orders of magnitude bigger. And you just even a hurricane has got 100 times more energy than the whole energy in a geomagnetic storm. And a thunderstorm or a tornado is about 1/10 of a geomagnetic storm. And if you look at how much energy is actually produced, it's about of the whole world electricity generating capacity. It's about the same as a geomagnetic storm. So you can see that you've got a lot of energy down there. If only a small little bit of that energy from the troposphere is able to propagate up and influence the the thermosphere and the ionosphere, you haven't got to get very much. And not very much does get up there in total power and total energy. But you don't have to get very much to see some significant effects. And I'll just show you a couple of examples of some of the signatures that you actually see. This is, again, a whole net. This is from Van Akim. And they have a whole network of ground-based GPS stations. And these are all the fluctuations of the total electron content. And so this is the ionosphere, the F region ionosphere, and the top side of the fluctuations, the detrended. So these are all the fluctuations in TEC that you see as a result. So these are all those waves that are propagating up from convective storms. And it turns out that there was a big convective storm down there in Texas, and it was creating all of these waves that are propagating out. You can see these concentric rings propagating out from these waves. So they're all creating undulations in the ionosphere, and they would, if you need, they would be like one of the sources that created the undulations that you need for the equatorial bubbles to form. So all of the little undulations, they're all creating tilts as well of the ionosphere. In the HF propagation that we're interested, we need this ionospheric layer. We need a nice layer for the ionosphere, for the radio wave to reflect from. But if that ionospheric layer is tilting up and down, then you're changing that propagation path. So the strongest signal won't be here. It will be, so you'll cause fluctuations in the signal power if you're using HF for propagation as a result of all of this impact of the waves coming from the lower atmosphere. And if you, this is a quiet period. Again, these are maps of the total electron content. These were actually during a quiet period. And then on this day, geomagnetic activity was low, solar activity was low, and yet you got this 50% increase in plasma density, this total electron content, this integrated plasma. So clearly we've got, and this is sort of where the equatorial ionization anomalies are. You've got this 50% increase in plasma. It was totally unexpected. We saw it at mid-latitudes on our US tech plots. That you see it when you map the TEC. So this is another, what we think is a response to changes in the lower atmospheric dynamics. This was a period where there was a sudden stratospheric warming. Normally, the southern pole, I should have had a figure for this, around the southern winter pole in the stratosphere, the winds are circulating around the magnetic pole, around the geographic pole. But sometimes the changes in the planetary wave cause that the rotation around the pole to break up into two vortices, so it splits into two. And that affects the way that tidal waves propagate up through the atmosphere. And you see the signature of the tidal waves all the time in the lower thermosphere. But you have a big change in the tidal forcing in the thermosphere and the ionosphere. And we think that's what's causing these changes in the plasma density. It changes the tides, it changes the dynamo action of those tides, because those tides get up to the lower thermosphere, where there's the strong collisions in the lower thermosphere between the winds that are propagating up and the ionosphere. So it changes the dynamo action of those tides. And we think that's what's causing these large increase in plasma density. So you've got these different things. So all these things can happen at the same time as storms, as a geomagnetic storm. So you can have a mixture of all of these processes. And that's one of the challenges for sort of the next generation coming through is to try to unravel when you have large changes that are coming from the lower atmosphere at the same time as you have a geomagnetic storm. So you have all these neutral composition changes at the same time you have these tides propagating up. So I think that's probably more in the sort of the discovery mode, if you like, to try to unravel the complexity of the forcing from the lower atmosphere. So I'm just going to try and summarize a little bit what I think some of the main points. You clearly see that we understand quite a lot of all of those processes that are happening, and the changes in the winds, the circulation, the composition, the negative phase, the positive phase. And really, at this stage, we're trying to understand the thermosphere-ionosphere as a system. It's more system science. You know, we've discovered a lot of we're still discovering new things, like we discovered with the new observation technique from GPS, that you've got these larger positive phases than in the total electron content than we realized. But we're more on the system science, in the same way that the troposphere is system science, trying to improve weather forecasting. They're not really sort of discovering the impacts of water vapor, but they're trying to improve the changes in water vapor during a storm, you know, a convective storm and things like that. So we're in the sort of system science sort of realm for some of the thermosphere ionosphere. So that, and so that as we saw that the electromagnetic energy is the dominant source at high latitudes. That's the Poynting flux that comes down the magnetic field into the upper atmosphere, and that creates the Joule heating. That's the dominant energy source. Of course, you have auroral sources, but that's about 20% of the heating. The aurora, of course, produces the conductivity increases, and that enhances the Joule heating because it changes the conductivity. So that there was a strong neutral dynamic response, and of course the dissipation of that electromagnetic energy is because you have collisions between the ion flow and the neutrals. If the neutrals end up just moving with the plasma, there's no dissipation. So the amount that the neutral atmosphere can actually respond to the ion drift influences the dissipation of this electromagnetic energy source down into the atmosphere in the first place. And then we saw that the neutral dynamics was a strong impact. It's the conduit for a lot of the things some of the things that happen. The wind surges, the changes in the global circulation, the changes in the neutral composition, the upwelling of the N2, and the subsequent impact on the ionosphere. So the neutral dynamics of the neutral atmosphere, which is obviously the dominant medium up there, is very important, as well as influencing the dissipation of the electromagnetic energy from the magnetosphere in the first place. We saw that you can get some really large neutral winds influencing satellite drag and generating neutral density holes. We saw the neutral composition responds to that large-scale storm time circulation that impacts the ionosphere, and we have seasonal variations, and that's particularly the negative phase is what is the dominant effect from that. But it has strong seasonal dependence and local time dependence, as we saw. But the electric fields, of course, the direct effects of the electric fields we now know are still important at mid and low latitudes, not just in high latitudes, driving with the ion drag and the Joule heating, but the penetration, the expansion of the convection pattern to mid-latitudes and the penetration to the equator are both redistributing plasma and doing that storage of plasma on the top side when the direction of the electric field is favorable. And so now we're seeing large regions of positive ionospheric phases. It's not everywhere, it's just in certain sectors, but there's large increases in the plasma density. We call that the positive phase. Traditionally, we used to call the ionospheric phases the negative phase and a positive phase. It just means a decrease or an increase in the plasma density, whether it's at the NMF2 at the peak of the F region or the total electron content. So, and of course, from all of this, we understand many of those physical processes. But the challenge is defining their relative importance during the various phases of the storm. And of course, they have local time effect, as we saw, if they're just in that noon dusk sector, has longitude dependence, because the region where the magnetic pole is more equatorward, in those longitude sectors, you generate a lot of longitude dependence in some of those responses. And of course, there'll be hemispherical dependencies as well. So that's sort of all the storm time effects, but then you've got the interaction between now we know that there's a lot of stuff coming from the lower atmosphere. You're going to have an interaction between all those lower atmospheric forces during a sudden stratospheric warming, and the waves from convection are going to superimpose and modulate possibly the response to the solar magnetospheric energy during a geomagnetic storm. So that's all I had. I hope it's given you a flavor of some of the range of physical processes. It's probably a lot to take in. But with the lab, I mean, you've got all this you can look back at if you're interested, and you can always go to the CCMC and experiment with some of the simulations if you've got a science question that you want to try and address. So that's all I had. So you can either ask questions or you can keep looking at some of those simulations. What have we got? It's coming up for 11:45, so we've got another 15 minutes if you wanted me to go through any aspect, any questions on any particular part of the... Otherwise, we'll have an early lunch. Good. Well, thanks for listening. I hope you got something.